Now, here's an example where I have a definite integral, but you have to confess, whether the Lagrange position is complicated enough to maybe where you and I can't, off the top of our heads, identify an antiderivative for it. However, if in the Lagrange position I have a nice clean power, that wouldn't be difficult. Notice how the power is this quadratic beast whose derivative really is what's out here as factor neglecting a numerical coefficient. Screams out at me that I can, number one, clean this integrand up by letting u be the exponent. Number two, that u is going to have a derivative as factor in the integrand's position, again neglecting a numerical coefficient. Let's give it a shot. So number one, pulling out the 5. Number two, replacing x dx with 1/6 du. It gives me this up front. So if you look carefully what I have on the inkboard, I have a pretty grave mistake. The mistake is this. If you interpret this question as an area question, excuse me, then I'm looking at finding the area of the curve y equals all this garbage as x ranges from here to here. But with the substitution, my u values aren't necessarily going to range to the same values. And so I sometimes think of this dx as identifying the variable of, identifying the flag to which I pledge my allegiance. Because I changed the flag to which I pledge my allegiance, everything else has changed. I changed everything except for my bounds integration. Technically speaking, my old lower bound integration for x is 0. Correspondingly for u, okay, so it turns out to be the same thing this time around. But notice how the old upper bound integration 1 for x, when I plug 1 in for x here, it gives me corresponding upper bound of integration for u to be 3. Now an anti-differentiate and evaluating. Now, if you don't like the idea that I changed the bounds integration, there is an alternative. So let me write the original integral. Whoops, rewrite it correctly. Some people insist on committing to substitution. They're too lazy to just identify how the bounds change. And that's fine. If that's the way you want to play this game, just tell me that it was the case that for x, the lower bound was 0, and for x, the lower bound was positive 1. And when I anti-differentiate, whoops, do it so you can read it. To use these values for x, I back substituted. Now I don't have to tell myself what x is because I've got this expression in terms of the variable x. And in evaluating, oh, thank goodness, I get the same answer. So the upside to this technique is you don't have to back substitute at the end. The upside to this technique is that you don't have to worry about how the bounds change. You're too lazy. You'd rather keep them as they are. Tell the reader you understand they're not bounds for you. And then back substitute so you can use those bounds that you initially had. Oh my goodness.